Hey, so I need to tell you about quantum teleportation. So this really isn't what you think. It's not like, Captain Kirk beaming people all over the place or whatever. But, because we haven't really been able to teleport matter yet. But we have teleported photons of light, which is pretty cool. So they first started doing this in 1998, and it was first done by a group of researchers at Caltech. So the way they did this was they used 3 photons of light. And they used a coaxial cable and quantum entanglement, which is something I'll tell you about a little later. But they were able to teleport a photon about a meter. So the way this kind of works, they had 3 photons. So they have photon A, photon B, and photon C. So photon A and B were connected by a coaxial cable, which is just kind of a cable used to transport information. And then B and C were entangled. So basically the goal is to get A to C. So the way they did this was they transported the information, or the quantum state of A through the coaxial cable to B, which then was transported by quantum entanglement to C. So at that point, C became A, that's an A, and A pretty much just ceased to exist because of conservation of energy in the universe. So basically, entanglement is, so when 2 photons or electrons or whatever are entangled, they basically are just they're kind of intertwined, but they're not connected like physically. So they kind of simultaneously know each other's state. So they're in a state of what's called non-locality. Now, non-locality, it describes the apparent ability of objects to instantaneously know each other about each other's state, even separated by large distances, potentially even billions of light years. So basically, if 2 photons are entangled, they can be anywhere in the universe. And if one of them changes state, the other one knows about it and instantly changes it too. So the way this works is with what's called spin. Now, spin is basically just angular momentum. So every object in the universe has has spin. It has some kind of angular momentum, even if it's not actually spinning. So you have a photon here and a photon here. So this photon has spin up. Oh, these are entangled, by the way. This one, since it's spin up, this one over here has to be spin down to conserve angular momentum in the universe, because if you had 2 entangled photons with the same spin, the conservation of angular momentum would not be there. Angular momentum would not be conserved. So then if this one switches to spin down, this one must switch to spin up to conserve angular momentum. So the way that 2 photons can be entangled is if a beam of light is split. The two of the photons that were in that beam of light, if they had come in contact in that beam of light, they are now entangled. So Einstein observed this and called it spooky action at a distance, because he didn't understand it all. He hated this. He did not support it at all, because basically the transferring of the state of the quantum state of the photons, it's transported or teleported, or however you want to say it. It's instant. It's instantaneous. But Einstein's theory of relativity says that nothing can move faster than the speed of light. So it clearly goes against that theory of relativity. So that's for that reason he completely hated it. He didn't support it at all. And that's kind of the main argument against teleportation. And I'll kind of talk about that more in a minute. So now along with the pattern of quantum mechanics, we're going to take this somewhat simple task and we're going to completely overcomplicate it. So now, say that in the quantum world, this photon right here has both spin down and up at the same time. But we don't know which one it is. It's actually both at the same time. Just like how Schrodinger's cat is both dead and alive at the exact same time, but you don't know which one it is. So since this one is either down or up, this one has to be either up or down. This one is either up, down, or up. It has to be whatever is opposite of this one. So by observing this one right here, you cause it to choose between either up or down, which then causes this one to choose between down or up. So basically, by observing this one, you're deciding what that one is. So this is kind of illustrated in a scenario known as the Bob and Alice scenario. So basically, let me erase this. you have Bob, and you have Alice. There's Alice right there. So basically, there's a beam of light, and it is split with one photon going to Bob. Here's Bob's photon. And one photon going to Alice. There's Alice's right there. Now, say they're looking over here at something else. They're not looking at the photon. This photon is now in a state of superposition. So, the beam of light rather is in a state of superposition. Because the beam of light, the two photons, which are components of the beam of light, are both here and here. So this beam, which is one beam is now two photons, is in superposition. It is in two places at once. Now, say Alice decides to look at this photon. She's kind of looking up at it. And that causes, so when she looks at that photon, that causes Bob's photon to completely just cease to exist. So by Alice observing it, it causes Bob's to just disappear. It doesn't exist anymore. So that's whenever the superposition of the beam of light collapses. So this is actually done in a lab. Or two labs, I guess. So they had a beam of light and they shone it through a crystal. And so one photon of the light went through the crystal, went to one lab, which is the Bob lab, and the other one reflected back to the Alice lab or whatever. So it was actually in both places at once, and then until one of them observed it, which then caused the other one to completely just disappear. So actually pretty dang cool. So now you're kind of wondering, will this teleportation exist or does it not exist? Well, it doesn't really, because the only thing that's being, like with quantum entanglement, the only thing that is being transferred is the photon's quantum state. So it's not really actual information, it's more just the two parts, or the two photons that are entangled kind of knowing the state of each other. So information, according to Einstein's theory of relativity, no information or matter can go faster than the speed of light. So that actually does agree with relativity, which is why it's people are not completely against it. But this isn't really practical, because there's no way, it's impossible to teleport matter. There's a few different reasons for this. Well, the main one is that basically teleportation works like a fax machine. So first step is the thing, whatever it is, the fax machine, it scans and measures the object that's being transported. It just learns everything it can about it, so it can build an exact replica on the other side. Then the information is sent to wherever it's going, and then when it gets there, it is reconstructed. So the problem with scanning or measuring the object is Heisenberg's uncertainty principle. This means you can't know both the momentum and the position of an object at the same time. So there is no way you could measure this and get an accurate measurement of it to send it over. And even if you could send it over, like a human has an estimated amount of 10 to the 29 atoms in its body, which is about a trillion atoms in the human body. So there is no way that you could reconstruct that. And yeah, it's just completely impossible. So there's no way that this can be used to transport matter. And even if you could, then there would be two of the same person at the same time. So yeah, I'm not even going to go into that because it's really complicated. And so there are some practical uses of this in the future. They're exploring possibilities of kind of using the same kind of thing, but with it would be kind of halfway between like speed of light and instantaneous. So it wouldn't be instantaneous, but it'd still be faster than speed of light. So although this does kind of violate Einstein's theory of relativity, he's probably not liking this very much. They're still trying to do it, but I don't know if it's going to work out or not. So that's about it.